Hello student, good morning. I am Dr. K.Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing review of gaseous state part 1 and I have discussed many terms like Joule-Thomson coefficient, inversion temperature, liquefaction of gases at critical temperature, relationship between liquefaction of gases and van der Waals constant. Now I will continue after that. Now next things I am going to discuss today, that is the methods of liquefaction of gases. Actually I am reviewing the chapter. Okay. Then now next I am going to discuss methods of liquefaction of gases. Then there are three methods of liquefaction of gases. First, Linde process. Second, Claudius process. Third, by adiabatic demagnetization. What is a Linde process? Then by this is done Linde process by adiabatic expansion of compressed gas. This is based on Joule-Thomson effect. Linde's process is based on Joule-Thomson effect, or you can tell by adiabatic expansion of compressed gas. This is the first method of liquefaction of gases. Second methods of liquefaction of gases, that is the Claudius process. This is done by adiabatic expansion of compressed gas involving mechanical work. Claudius process is based on adiabatic expansion, or you can tell by adiabatic expansion of compressed gas involving mechanical work. Now third one I told you, that is the adiabatic demagnetization. These are the methods of liquefaction of gases. Now next point, that is the general equation of a state of real gases. General equation of a state for real gases, that is the Camerlin oneness equation, that is also called virial equation. Question is asked. Virial equation, what is the virial equation? It is called actually general equation of a state for real gases, also called Camerlin oneness equation, ONNES, oneness equation, also called virial equation. Here PV is equal to A plus BP plus CP square plus like that. Okay, again I am telling you, general equation of a state for real gases, that is also called virial equation, also called Camerlin oneness equation. This is PV. PV is equal to capital A plus capital B into P, capital P, plus CP square plus dot like that way. Means it is focusing on pressure. Always pressure power is increasing. PV is equal to A, capital A, no pressure term is there, only A, plus BP. Now P is introduced, plus CP square. Now P power is 2, plus dot like this. What is the ABC? Then A, B and C are called virial coefficients. Virial coefficients. At very low pressure, only A is significant. This is the important point. For very low pressure, if pressure is very low, only capital A is significant and is equal to RT. At very low pressure, PV is equal to RT. At very low pressure, only A is significant and is equal to RT. The second virial coefficient, that is the capital B, is negative at low temperature. The second virial coefficient, capital B, is negative at low temperature. With increase of temperature, it increases to 0, from negative to 0. At low temperature, I told you, B is negative at low temperature. With increase of temperature, it increases to 0 and then becomes more and more positive. The temperature at which B is equal to 0 is called boil temperature. You remember, correct? With increase of temperature, it increases to 0, negative to 0, and then becomes more and more positive. The temperature at which B is equal to 0 is called boil temperature. Now, next term, I am telling you law of corresponding states. Law of corresponding states. Pressure, volume and temperature expressed in terms of their critical values and are written as capital P is equal to pi into PC, and V is equal to phi into Vc, and T is equal to theta into Tc. Here P is equal to pi into Pc. You remember, pressure, and PC, that is C means critical. Then PC means critical pressure. Then P is equal to pi PC, first relation. And volume, capital B is equal to phi Vc. Vc means critical volume. Vc means critical, V means volume. Then V is equal to phi Vc. And T is equal to, T means temperature, T is equal to theta Tc. Tc means critical temperature. Then here Pc means critical pressure, Vc means critical volume, and Tc means critical temperature. Then there are these three relations you remember. P is equal to pi Pc, and V is equal to phi Vc, and T is equal to theta Tc. Hence, now you can write pi is equal to, when P is equal to pi Pc, then pi is equal to P upon Pc. Similarly, V is equal to phi Vc, then phi is equal to V upon Vc. Similarly, T is equal to theta Tc, then theta is equal to T upon Tc. Here, pi, phi and theta are called reduced pressure, reduced volume and reduced temperature respectively. You remember what is the pi, phi and theta? Then pi, phi and theta are called reduced pressure, and phi is called reduced volume, and theta is called reduced temperature. Correct? Pi is related to pressure, you have seen. That's why it is called reduced pressure. And phi is related to volume. That's why it is called reduced volume. And theta is related to temperature. That's why it is called reduced temperature. Then pi, phi and theta are called reduced pressure, reduced volume and reduced temperature. If two substances have the same reduced pressure and same reduced temperature, they must have the same reduced volume. This you remember. If two substances have the same reduced pressure and same reduced temperature, they must have the same reduced volume. This is called the law of corresponding states. This is called the law of corresponding states. Now next term I am going to discuss critical constants. Critical constants in terms of van der Waals constants. Here critical constant means Vc, Pc and Tc. These are asked in examination. Value of Pc, Vc and Tc. Then here Vc is equal to, critical volume is equal to 3B. You remember. Critical volume is equal to 3B. Critical pressure is equal to A upon 27B square. And Tc is equal to 8A divided by 27 RB. You remember, always these questions are asked in competitive examination. For just particularly for IIT and medical, this relation is asked. Vc is equal to 3b, small b, and Pc is equal to small a 27 by 27 b square, where A and B are van der Waals constant, and Tc is equal to 8A divided by 27 RB. 27 is common in both Pc and Tc, and A and B again common. Pc is equal to, actually Vc is equal to 3b, correct? And Pc is equal to A upon 27b square, and Tc also 8A upon 27 RB. Here in the place of b square, R and 1b is there. Okay, R and B. R is extra and B square was there, that is only B. And upside 8 is there. This is the difference from Pc and Dc in expression. Pc is equal to A upon 27 B square and Tc is equal to 8A upon 27 RB. How they are related? Next point. How they are related, Pc, Bc and Tc? This is also very, very important question. This question is also asked in examination. Relationship between Pc, Bc and Tc, all three. Then Pc into Bc, it is related, relation I am telling you. Pc into Bc is equal to 3 upon 8 RTC. See, again I am repeating, Pc into Bc is equal to 3 upon 8 RTC. And next point, that is the heat capacities at constant volume and at constant pressure. Heat capacity at constant volume, that is called Cb, and at constant pressure it is called Cp. The amount of heat required to raise the temperature of a substance through 1 degree centigrade, keeping the volume constant, is called heat capacity at constant volume. Similarly, if pressure is kept constant, it is called Cp. Again I am repeating, the amount of heat required to raise the temperature of a substance through 1 degree centigrade, keeping the volume constant, is called heat capacity at a constant volume. Similarly, if pressure is kept constant, it is called Cp. Means Cp is similar to Cv, only difference is at constant pressure. Cv means at constant volume and Cp means at constant pressure. Then Cp also you can tell the amount of heat required to raise the temperature of a substance through 1 degree centigrade, keeping the pressure constant, is called heat capacity at constant pressure. Same type of definition, one is at constant volume and other is at constant pressure, and in both cases heat required to raise the temperature of a substance through 1 degree centigrade. Then now what is the expression for Cv? Then Cv is equal to critical volume Cv, not critical heat capacity. Heat capacity Cv at constant volume, that is equal to delta E upon delta T, or you can tell del E upon del T. Del is used for a small change. Then Cv is equal to del E upon del T, and outside down you can write V means at constant volume. Then Cv is equal to what? Del E upon del T. You are dividing by del T. It means per degree temperature, how much energy changed at constant volume. Then you can write del E upon del T in bracket, and down you write V. V means that means at constant volume. Similarly, for Cp, here you can write del H, enthalpy. Again same way, del H divided by del T at constant P. Means pressure. You are knowing here H is equal to E plus Pv, but at constant volume only E you are considering, and here del H means E plus Pv means work done also you are considering. H means heat enthalpy. Enthalpy is equal to E plus Pv. H is equal to E plus Pv. Then in Cv only E you are considering. Here Pv, P into delta V, work done, that also you are considering. Then here it is the del H. Cp is equal to del H upon del T at constant P. And also you should know Cp minus Cv is equal to R. Always Cp is greater than Cv. Why? Because in Cp that is heat required to raise the temperature by 1 degree centigrade, that is only involved in Cv. But in Cp both two work it will do. First it will heat required to raise the temperature by 1 degree centigrade plus work done. Because gas will expand. Then for expansion work will be done. Then that is the P into delta V, means change in volume. That's why Cp value is more. Cp value is more than Cv always. Because in Cp at constant pressure volume will increase. Then to increase the volume heat will be required, and then temperature will be 1 degree. Hence more heat it will absorb. That's why Cp is greater. Heat capacity at constant pressure is always greater than Cv, because in Cv only you can say volume will be constant, then only heat required to raise the temperature by 1 degree. But here both are required. Heat required to raise the temperature by 1 degree plus in additional heat required to do the work of expansion, because gas will expand. Hence always Cp will be greater than Cv, and difference is called R. That's why Cp minus Cv is equal to R. for 1 mole of an ideal gas. And another important point here related to this, Cp upon Cv, ratio of these two are called gamma. Cp upon Cv, its value is called gamma. And for monoatomic gas, example of monoatomic gas means inert gases, helium, neon, argon, krypton, xenon. Correct? Monoatomic gases. Then only this last group 18 means inert gases. They are only in monoatomic gases, no other gases. Only they are one atom. They are atoms, but they are gas. Then for them, its value is Cp upon Cv is equal to 1.66 for monoatomic gases and 1.40 for diatomic gases like H2, N2, O2. Correct? And 1.30 for triatomic gases like CO2, CO2, total 3. In after that CO2, NO2, correct? Then for NO2 also, that is, these are the three concept three atoms are there, they are in gas. Then for the triatomic gases, its value is given 1.30. You remember, question is asked. Then here three questions are related. First, you can say Cp minus Cv is equal to R for 1 mole of an ideal gas, and ratio Cp upon Cv ratio, that is called gamma. Then its value is 1.66 for monoatomic gases and 1.40 for diatomic gases and 1.30 for triatomic gases. Correct? Then here I have completely this reviewed the entire chapter. Okay, and next class I will just discuss further relations. Some relations are there, and many formulas are there that will help in solving the numericals. Okay, for IIT, JEE and medical. Okay, then keeping in mind this competitive examination, I will again revise all, you can say, important formula relations, and then I will switch over to the numericals or multiple choice question. Thank you.